Thanks everyone, thanks for coming, even though I think I was only on the schedule as of about 20 minutes ago. Yeah, I think there's going to be some good content in this that's hopefully interesting and useful. It will not be the smoothest presentation. The talk starts with a story, you know, like all good talks should, but the meta story starts with me being asked to present this content when I was hanging out with my friend yesterday evening, except that friend lives in Toronto. But here we are. So I want to talk about zero trust. I've called it Zero Trust Beyond the Buzzwords because I think there's a lot of hype and a lot of buzz around zero trust, right? Zero trust architectures and what that means, and a lot of vendors trying to sell solution, and a lot of marketing that's kind of lax on the details. So I want to go through essentially some sort of definitions and some bullet point lists that can help us understand this more. I'll touch on how we might implement it, but this is more going to be sort of stepping back and thinking, what does it mean to have a zero trust stance? Mostly on the network, but I will talk about compute a little bit. The abstract promises a lot of compute. I didn't have that much time, but I'll talk about the compute side of things a little bit as well. So if we think about a traditional network, you know, maybe Bob is running a network. This is exactly, you know, how he was told to do it, just like the book said. These are the best practices, just like the vendors told him to build this network. So you've got a firewall and a DMZ, and then there's another internal firewall, and you can hang some subnets off that, but actually firewalls are expensive and maybe a bit slow, so most subnets get just hung off a core router. So there's absolutely no access control between the things that are just routed, right? And then there's sort of subnet to subnet access control, maybe IP to IP access control between the things hanging directly off those expensive firewalls. The problem is, you know, some bugs are so bad they get logos. So these were meant to come in one at a time, but we've got a shell shark and a heartbleed. Apparently that's the official Log4Shell logo. Oh, wow. Apparently that's what happens. That's what you get if you Google it. And then your Cisco Edge device might have a 9.8 because it just has a default root password. Your Fortinet, you know, not to pick on any one vendor, your Fortinet Edge device might have a 9.8 because you can get full remote code execution pre-auth with a misformed packet. So you kind of have to assume that the attack is already in the network. This post-it note here came out of the Snowden leaks, actually. And this was the NSA's drawing of how Google works and where they were inside Google's network. And the little smiley face is them complaining that Google has the audacity to put TLS on things in some places, but not everywhere. So this is how Google found out that there was an advanced persistent threat inside their network. And, you know, all of those adjectives are actually sort of applicable. So, you know, it's not really Bob's network, maybe it's Eve's network, right? And if your attacker's already in the network, then, as I say, there's very little security inside of these things because you've got past that edge, which is where we traditionally do security boundaries, right, and trust. So if you're in one app, you can just talk to another, and there's often nothing to stop you. So trust no one, right? We have to labor under the assumption that the attacker is already in the network. Right? They are advanced, they are persistent, they are probably threatening us. So that brings us to doing zero trust. But what does that actually mean? So maybe Bob can go and build a better network, right? So this is kind of what it looks like now. And the difference is those sort of central firewalls have gone, and what we've got is a policy decision being made and being enforced at every hop. Right, at every possible request. So for every pair of services that want to talk to each other, we can make a policy decision and we can enforce that policy decision. So that looks like a PEP, a policy enforcement point, with every app, right, whatever that means. So there's essentially a firewall everywhere, right? Everything you kind of have to treat like it's the front door. And it's no longer good enough for traffic to arrive from a privileged position and be trusted, because privileged positions don't mean anything anymore. In fact, you know, there aren't any. That old perimeter model is dead. And importantly, with the more modern technologies we've got, the policy that we want to apply for this can be codified and automatically, you know, enforced everywhere. So what are the principles of this zero trust, right? We need access control between every pair of services that is least privilege. So, you know, any workload can only talk to any other workload that it's meant to, right? It sounds obvious, but if you don't have any kind of policy enforcement, if you don't have any kind of firewall between a particular pair of services, you just can't do it. So any request that tries to follow one of those, you know, routes that isn't ordained is either a mistake or it's malicious, and both of those need to be blocked. And in order to do that, like I say, you have to, you know, get down to enforcing policy everywhere. It also has to be per request. So this is sort of least privilege in time rather than least privilege in space, right? You know, one request from a workload to another workload might be valid, but then the next one isn't, because it might be a different operation, your access might have expired, there might be a rate limit to avoid, you know, sort of DOS scenarios, that kind of stuff. So no more, you know, setting up a flow and just leaving it. So no more, you know, network 5 tuple of can this TCP port talk to this TCP port. So that means whatever's doing your inspection and you're making your policy decisions has to understand what it's seeing on the wire. It has to actually understand the protocols. You know, maybe you've got gRPC in HTTP2 in TCP. If you're going to do per request, you need to be able to pull apart that HTTP multiplex, and you need to understand the semantics of gRPC. You know, what's a read and what's a write, and what endpoint, you know, what gRPC service and method are you targeting. Access control needs to be identity-based, so it's no longer, you know, based on the location, which you might try to identify by the network or the IP. We have to give it a strong, you know, cryptographically strong identity. We have to give that identity to something, and I'll talk a bit more about that later. And it needs to be context-based as well. We need to be able to make those decisions about whether we allow something with a little bit more context rather than just A is trying to talk to B. You know, it might think about previous requests that have come in. It might know about the state of the system. If we combine all the techniques I'm going to talk about, then, you know, you can say something like, well, the back end can talk to the database, but only if that request came to it via the front end, and only if it's on behalf of a logged in user who has a particular read permission, right? So we're talking about the machine identity there. I'm skipping ahead a bit. But we're talking about the sort of machine identity of backend and database. We're talking about the user identity of, you know, are they logged in? Who are they? What scopes do they have? So what are we trying to do with this better policy? Well, we're trying to bound attacks in time, kind of skipping ahead to the implementation here. You know, if you can steal some creds, often you can replay them. There's a lot of cryptography, a lot of advanced, clever security people, you know, have stopped various of those attacks, but still, if you own a workload and that workload has creds, you can impersonate that workload. So automated issuance of certs or whatever your identity is going to be, and automated fast rotation of them to sort of bound these attacks in time. So if you get into a workload, any creds you steal, any impersonation you do won't be valid for very long. And then bounding attacks in space, which is basically preventing pivoting, right? If I get into one workload, I then can't move laterally. It's, you know, it's as old as time, but you have to have all of these previous things, because all of these things actually say, well, what is a valid request from one service to another? Nothing else counts, and anything else is just a potential vector for lateral movement that we want to block. So how do we, sorry, first time I've been through these slides, no idea how long they take. How do we control for this, right? How would we enforce this? So one of the main ways we do that is at runtime, right? On the network, because we are talking about network requests. So if there were sort of 5 pillars of zero trust architecture, I think it's this. This is hopefully trying to get beyond the buzzwords to what do we actually mean. So we need encryption on the wire of these requests. We need service authentication. I'll go through all of these. We need service-to-service authorization, we need end-user authentication, and then we need to authorize the end-user to a particular resource. For anybody who's not familiar, authentication is sort of, you know, who am I? It's my, you know, I've got my passport on me. I wave my passport to prove that I'm Matt. Authorization is, well, now I know who you are you allowed to do something? So does your passport contain a visa for this country? It's all very good that I trust you are who you say you are, but you're not allowed to enter Australia. So this encryption on the wire, well, this prevents interception. You know, data might be sensitive. We might not want them to be read. It also prevents tampering, because all of the other controls, all of the other claims are useless if you can't trust the bytes that have been, you know, coming over the wire. So reading the data is bad because you might steal sensitive information. Reading the metadata is bad because I might be able to steal some creds and replay them. And if I can tamper with that data, I can break your system, and if I can tamper with that metadata, I can bypass your access controls, probably. So once we've got that foundation, service authentication, so one service knowing who another service is. So by service, I mean sort of a workload, like the sort of machine identity. So yeah, this is workload to workload. Like, can the backend talk to the DB? Would be a kind of access control question we would ask. And you can couch that in standard, you know, like RBAC, right? So you've got your, it's basically verb, it's basically object, subject, verb, right? So you've got your, what would Amazon call it? Your principal and your action and your resource. But those three things, can the backend talk to the DB? There are some standards, again, skipping ahead maybe to how you'd implement this, there are some standards for encoding this kind of thing. Spiffy is the main one and talks about a way of making, minting IDs for workloads with a bunch of useful properties that I don't really have time to go into, that can then be embedded into JOTs, into X509s. It's implementation agnostic, but they've got some reference ways of doing it. Issuing these things should be a really high bar. I'm going to come on to that, but this is where a lot of the heavy lifting is done. Because obviously impersonating a workload is quite a common thing. This is why we have SSL on the internet and so forth. Once you know who the workload is, then we can talk about authorization from service to service. We know we've got the back end of the database. Can one talk to the other? Can one perform a read operation, a write operation? End user authentication. This is I guess fairly straightforward. Do we know who the end user is? They're probably not going to, if you're in your browser trying to buy some tat for Valentine's Day, you're probably not going to present an MTLS cert, right? So we're probably going to log them in, and then that OIDC flow will exchange that for a JOT, or you've got some way of identifying the end user. And then when we know who the end user is, we can authorize them. But we don't talk about authorizing them to the workload. It's not, can this user, can I talk to the database? Well, of course, requests on behalf of me, requests when I'm logged in can talk to the database, but that's not really good enough because I shouldn't be able to read somebody else's records. I shouldn't be able to perhaps even write to my own records. I shouldn't be able to set the balance on my credit card higher. So we need to talk about authorization of that end user in terms of resource. So the nouns and verbs of your application layer, of your business logic, because that's what you're trying to protect from humans. The other places we put controls in to get this zero trust is the sort of the people and the processes. So yeah, I said the minting of these workload identities. Sorry, there's a lot of text on this, not the smoothest presentation. But essentially saying that if I'm going to give back end one of these spiffy IDs or something that identifies it, that lets other things believe who it is, well, what do we need to look at? I need to look at verifying the machine that this thing is running on. So on an on-premise server, I might talk to its TPM. Cloud provider VMs have got identity documents. A phone's going to have a device ID. Those things are sort of cryptographically quite strong, sort of untamperable. They're a challenge response chip on the phone, I think, right? You can't sort of extract the key from them. So we need to know what machine it's on, because this is, if I think that a copy of the very important ledger service is talking to me, well, is that running on our server in our SCIF, or is that running on a random Chromebook in Russia? Because that's actually really important. It might be the right binary. Things get stolen. The attacker's in your network. It's a really important distinction. And you can do clever stuff like sort of impossible travel detection, which I think I just failed. You then also need to look at the human, not the end user, but the human that's trying to execute this workload, right? Before you mint this thing in ID, have they verified their credentials recently? What device are they on? What location are they in? Have they been fired? Your offboarding procedure should very quickly shut down somebody's ability to check in code, to build code, to interact with CI, and to run any of your binaries. At least, not to run them, probably, but to run them in such a way that they get minted, a cert that actually means something. So yeah, do they have the permission to go through all of those steps of the build? So if I do a git checkout, if I've done a dev build of something on my laptop and I try to run it on a production server, maybe that probably works, but it should only get a test ID. Likewise, if I've managed to get my hands on a production binary, a production build with all that attestation that's come through the CI system, but I'm running it on my laptop, it should only get a test ID because it should be restricted in what it can do. Only a production build on a production system should have the full production access, because to get that build onto that system, you've got to go through a bunch of gates. So then you can issue it an identity you probably actually trust. Some of these are maybe a bit blue sky. It's not obvious for me to tell you how to go home and implement them straight away. I know it is possible. Like Google does all of this stuff. I'm sure other companies do as well. Off the top of my head, I couldn't tell you open source projects that get all of them, but there's obviously standards like Spiffy and OAuth and JWT behind all of this stuff. And YubiKeys are great and whatever. And then you actually need to verify that binary that you're running, right? I've verified the machine that it's trying to run on and the human that's trying to run it. This is where we get into more of what I'm probably going to talk about later, which is, well, what's the build signed? Does it have an SBOM? Was that SBOM signed so that I trust it? Is that SBOM, what's an SBOM? It's just a very long JSON document. Is it within policy? Does it actually contain violations that I care about? So how might we implement this? This is just going to be a slightly quicker one. It's not really what this is about. You need to get that implemented. You need to get that policy decision and policy enforcement, and they can technically be separate. Like all the academic literature refers to PDP and PDP, policy decision point and stuff. But you need to, usually they're the same thing. You need to get them with every workload. So there is obviously many ways to skin a cat. The obvious ways of doing it are either some kind of fat client library like Spring or gRPC, that's got auth middleware, auth-n middleware, auth-z middleware, knows how to talk at MTLS. Or you have your app be done when you use a service mesh like Istio or Linkerd. In terms of a service mesh, I just want to mention that approach because they're Kubernetes native and quite easy to operate in a cluster, but they can also run on traditional hardware. So if you've got stuff on VMs, you have to go do your own plumbing, your own IP tables and whatever, but you can get, in Istio's case, you can get an Envoy and you can put it on VMs, and it can then be the policy enforcement point for more traditional workloads, and you can get them talking to each other under this unified, control plane, under this unified policy. So that, the same would be true of gRPC libs, right? But you're probably retrofitting stuff, especially if you're going onto legacy hardware, traditional hardware, sorry, try not to insult anybody. So maybe a service mesh is the way to do that. I do have to pay my rent, right? So I work for Tetrate. If you do go the service mesh route and you take Istio, you will hit scaling problems with it. Technical scaling problems, people scaling problems, policy scaling problems. We make a management plane and a nice abstraction that will save you from that. Right, this is the bet that we've taken in this technology space. You might also be regulated or want to meet certain standards, and all of this stuff is very useful there as well. So the US federal government's actually done a lot of work in this space. There was an executive order from the White House, I don't know if the White House spokesperson's in here, on improving the nation's cybersecurity, which is basically saying, please do microservices, microsegmentation, zero trust. And then NIST came out with some special publications kind of telling you how. So 207 talks at a high level about zero trust architectures. 204 tells you what a microservices system should look like. And then 204A specifically says, right, here's how to use a service mesh to do that zero trust using microservices and using a service mesh, and there's even a mapping in the appendix between all the controls in 204 and like the Istio features that you want to go and toggle on. So if you're subject to regulation that's telling you to do this stuff, or you just want some guides and some guardrails, then there's actually a lot of quite practical advice out there, especially in 204A. It's probably better than you think. And then I know we're in the UK, but the US banking regulator, FFIEC, basically just adopted NIST 800-204 wholesale to tell banking how to do it. They took that as a good reference. I'm steaming ahead of time. I didn't bother to pull the demo out. Well, I wasn't brave enough to get the demo out. Oh well, you'll have to listen to me talk. So on the other side of zero trust, right? So I think we've had the obvious definition of don't trust the network, right? And hopefully I've gone into what that actually means in terms of you need encryption on the wire and you need service and end user, auth-n and auth-z. But we can't trust compute either, right? We have to have sort of zero trust on that side of things as well. So beautiful 4 a.m. diagram here. This is a container image. What's not to trust about a container image? Well, first of all, it's the computer it's running on. I've touched on that a bit. I won't really have time to go into this, but it should be, if we've done the architecture that we talked about before, it should be protected from its neighbors. Other workload. If you run this container image on one of those servers, say in a Kubernetes cluster, other other workloads in the system shouldn't be able to talk to it, because we've talked about, the sort of pillars of zero trust across the network, because that's how they're meant to communicate with each other. But there's always side channels, right? It doesn't protect you from that architecture doesn't protect you from noisy neighbors trying to DOS you. It doesn't protect you from any of the more privileged parts of that system, like being owned, right? So the Docker daemon or the kernel or the libc on the host or the BIOS or any of that kind of stuff. So we have secure boot and we have TPMs and we have all of that good stuff. Not really the topic of this, because what I wanted to talk about was trusting your supply chain or not trusting your supply chain, because I think this is the biggest vector, and this is a really easy way for people to come in from outside your organization. When they're trying to attack the network, they can knock on the front door, and if you've got a misconfigured firewall or you've got a CVSS 10 in one of your perimeter devices, they'll get in. Getting into the BIOS, it's not to say that certain organizations can't get into the BIOS of these servers, but again, it's easier to hit the supply chain, and we've obviously seen a lot of that. So your container image is going to have several things in it. It's going to have your app, which I've kind of sort of highlighted in blue here. And then the container image is probably going to have a libc, and it's probably going to have a libSSL. Maybe you're building, completely statically linked, Rust or Go or something, but even Go links against libc more often than you like it to. You really have to tell it to stop. So you're likely to have these other things. CA certs is something that's often overlooked. It feels like every month, a new root CA authority in the web PKI is found to be a dodgy front company or a nation state or somebody that we don't want to trust, and it gets yanked from that bundle. But nobody ever checks the online certificate revocation lists, right? So it really relies on how recently was your image built, how up to date was your CA certs package, have you had a version of that package where that thing's been yanked. So that's something that we can now do. Jetstack did a little tool where you can replace those at runtime, basically, right? And then you can block list in much more real time. But even, apart from CA certs, which is, I think, often overlooked, you're going to have, like, some binaries. What was I going to say? Yes. Right, okay, yes. Sorry, jet lag. But we have to trust something, right? I mean, I've talked about zero trust networks, but it's trusting nothing without verifying it. I don't know the Russian off the top of my head. But obviously there are some things you trust, because there's some things you want to talk to, but you need to verify, take a load of steps to verify that is what you want to trust and not trust anything else. And it's the same with the contents of your container image, with the code that you're going to run. We do want to pull in a bunch of packages. We want to use open source. This is what this whole conference is about. But we want to verify those things, and we don't want to trust anything else, anything that we're not happy with, anything we've not looked at. So again, it's about getting this down to the smallest set of things possible, and then attesting the things that we have left to say that we do trust them. So your app, for example, is likely to have a bunch of dependencies. If this is Go, heaven forbid you link against like the Kubernetes API, you're just going to have like 1,000 dependent packages or something, right? And all of these other things like libSSL does as well, I'm sure, but that's maybe less of a concern. But your app's going to have a bunch of dependencies. So you can come along and you can sign the container image, as the lead engineer, or your CI system can do it. But what does that mean? It just means that this big tarball of tarballs has passed across your desk, right? I mean, so it means that whoever runs it is running the one that was on your machine that you signed, but it doesn't often mean much more than that. It tells you that this image isn't completely completely unknown thing off the internet, but it's probably full of completely unknown things off the internet. So the normal approach to this is a document, right? An SBOM, a software bill of materials. Again, I didn't get a chance to do a full treatment of this, but I think this is really important. And you can think about it in the same way as we think about network zero trust. So you can get this software bill of materials that's going to tell you what's actually in your app, all of the transitive dependencies, what's actually in your software. And this can help you reason about it, and this can be checked against CVE databases, and this can be given a policy for even open source licenses that you do and do not want to accept. It needs to be signed to be useful, otherwise you just can't trust its contents at all, but that's necessary, it's not sufficient. Again, just signing an SBOM, which is a huge JSON document that comes across your desk, isn't going to do much. So you need to think about it, you need to reason about what's in it, and actually your CI system should be signing it anyway. And I think one of the reasons we struggle to reason about what's in these containers, because I'm going to get onto the implementation, maybe some practical tips about how we solve this. One of the reasons it's difficult to reason about what's going on is because the way we build containers normally is we build them up in layers. We have a Docker file that builds them up in layers. Each one of these is a new run command that's going to say, yum install, or it's going to copy something in or run an arbitrary piece of script. So each of these layers is imperative. That run command can have any piece of bash that does anything. Often people just call apt install or yum install, but those packages too can actually contain arbitrary script in their pre and post install hooks. And these things are Turing complete, so decidability problem. No way of ever knowing what they do. No way of completely statically analyzing them. And what I've tried to show here is we've got maybe the base image, and then we've got another layer. We've run a run command that's going to install, an updated version of a package, or like a package that's going to mask some of those files. And then we've got another layer where we've copied our app in, from build. So it gets quite dicey to reason about what's in there. So again, we want to take a sort of declarative approach that can be codified and that can be verified against a policy at all times. So it's better to think about building these images horizontally rather than vertically, right? Think about what packages you want to end up in the end image, not the steps you want to take to get there. And if we're going to take that approach, so we basically want to give a declarative list of packages, right? Is the spoiler alert. And if we're going to do that, it would be great to find a packaging format that doesn't allow those pre and post hook scripts, that doesn't allow any kind of arbitrary scripts up front, that would say, do like a constraint satisfaction. So you give it a list of the packages you want, it runs CSAT over all of them, make sure none of their files clash, works out exactly what the end image is going to be, and then just renders it out in one fell swoop, right? You could never end up in a broken state where the second package clashes with the first one. You can never have hook scripts doing arbitrary things that you don't understand. It turns out that package system actually already exists, and it's APK, which might surprise you, because maybe Alpine Linux is not your favorite thing. Actually, more likely, BusyBox is not your favorite thing, and you're blaming Alpine for that. But APK is actually really good and has a bunch of these desirable properties. So people have built some tools on top of that. So if you think about, how might I do this? How might I build a container image? You could use a Docker file, very standard, very well understood, but it's got that kind of layering, masking problem that we've talked before. You could use Bazel if you hate yourself. You could use Nix if you're smarter than me. Nix is not a bad system, right? But it's quite niche, and it's got a massive learning curve. Then there's these tools, there's KO, which is for Golang, and Jib, which is for Java. They're kind of special purpose tools that take you, they're like a build system and a container build system. So they'll take your Go code or your Java code, and they'll get all the way to a container image. So like Java-C will emit you Java bytecode, which isn't very useful at all. The main Java command will wrap that up in a jar or a war or something for you. Jib will actually just wrap that in a container image, because container images are a packaging format at the end of the day. Right? Containers at runtime and the isolation that they do is something different, but a container image is essentially a packaging format. So Jib does that for Java, KO does the same thing, takes Go source, gives you a container image. So it's all declarative, there's no imperative steps in there, there's no layers. So ChainGuard have come out with these tools at the bottom, which is a more generalized version of that, which is what I basically wanted to get to. So AppCo, APKO, is exactly the program that takes the declarative list of APK packages that you want and gives you a container image in one step. So you can say, okay, I want base, and I want libSSL, and I want up-to-date CA certs, and I want TZ info, and I want, lib something else to do Korean translation, who knows. I want all of these packages in my thing. And again, no imperative steps, no chance for scripts, nice package manager. So that'll give you one step to a finalized container image. That gives you all the packages for all the other stuff except for your app, right? How do you get your app in there? Because we're not allowing arbitrary file copies. We're not allowing arbitrary scripts. So Melange is another ChainGuard tool that is kind of like a generalized version of KO or Jib. You give it your build, whatever your software build is. You call your build tool, and it'll basically go and sweep up the output. You say, hey, I'm going to do a Rust build, and the output ends up in .target/release. So go scoop up the contents of that directory, and then that is a APK package. So you can then just go in, you can build your own thing locally, and you can then install it into your container image, as an APK package alongside the one for libc and alongside the one for libssl. What are those packages? Well, because I've talked about SBOMs, right? This is kind of why we're here. If we're actually talking about trusting the software supply chain, knowing what's in it, enforcing policy over it, all those packages that we install need to come with SBOMs, and we need to be able to trust them, right? And they need to be built in sort of best practice kind of ways. So that's what Wolfie is. Wolfie is basically a repo full of APKs. So if you think about Ubuntu uses deb packages. It uses the apt program to install them, but they have their own repos. There's, repository.ubuntu.org or whatever it is. They have Ubuntu flavor Debians, and that is the Ubuntu operating system, basically, is an install of a bunch of Ubuntu packages. They happen to use deb as their packaging format, but it's installation of a bunch of Ubuntu packages. Alpine is an installation of a bunch of APKs, but they're the Alpine APKs that the Alpine folks have built, right, to their kind of to the way they want to build them. So Wolfie is another set of APKs, but it's built by the ChainGuard folks. They're more minimal, they're built in very secure tested environments, and they all come with an SBOM. So it's kind of like an OS, except they don't give you a package for a kernel, and they don't give you a package for a bootloader, so you can never actually run it on a bare metal system, but it's everything else. So everything you'd ever need for a container image. And as I say, it uses APK deliberately. So that actually that's not so bad. I think that's kind of what I wanted to talk about. Again, that's the implementation. I think those three tools are really good. I've got a whole talk on them. There is a demo that works, I promise, but I don't have the energy for it. But yes, we have seen the problems with traditional, like perimeter-based network security, the principles of what the zero trust thing actually is, how we control that at runtime with our R5 pillars on the network, how we also need to, I'll say it, shift left, step back and look at the things that feed into that before we get there, how you might actually take that away and implement it, the regulations and standards that might help guide you, and that you might automatically start ticking boxes of if you take this approach, which will make your regulator happy if you've got one, and then apply the same kind of model to supply chain security, trust nothing, and then how do we start testing things, and what does it mean to actually not trust nothing, but to trust the very minimal set of things and to trust them highly. So I hope that was useful and not too rambling. Thanks.
Thanks, Matt. So do we have any questions from the audience?
I'll do my best.
Yeah, I hope you're okay with that.
Yeah, it's fine.
I have a question which might be a bit specific. So do you know, it might also be a question that I should probably ask ChainGuard, but for Wolfie, do you know if they're maintaining old versions of packages? I think this may be something that as a security person is a bit of a niche sport, but I quite often want to find a specific old version of something that has a vulnerability because I want to prove it. But package managers typically don't keep those packages around. Do you know if they do that?
I don't off the top of my head. I'd imagine you could either get them from some mirror. They probably wouldn't want to make them available, so you couldn't make a mistake. You could probably get them out of the Internet Archive, I guess, or they build all their own stuff with Melange, so you could probably go write your own Melange file to take the GitHub repo of whatever it is and then build it yourself. It might not be byte for byte what was running if you wanted to prove a proof of exploit, but that would be that's the guess, to be honest. But it's a good point.
Cool, thanks.